again, and we should start now with the session. So the first presentation is under the title, The System for Monitoring Deformations Processes in High-Rise Material Structure. If I seen it well, Mr. Shardakov will present that. Am I wrong?
Hello, colleagues. I would like to introduce a team of researchers from the city of Perm, Russia. My colleague I.Shardakov is our team leader, and I, Irina Glot, will tell you about our results. First of all, I'd like to thank the organizers for the opportunity to participate in your conference online. It is very important for us. Now I share our screen. You see?
Yes, we can see it.
Now we can see an important trend in the design and construction of complex engineering and building structures. Such structures are often equipped with automated systems for monitoring their deformation state. In this report, we would like to present our automated system for deformation monitoring of high-rise metal structure. This monitoring system we have developed and installed. We also show the results of using this monitoring system obtained over 3 years of its operation. The monitoring object is a metal structure of overhead building of the skip shaft. This facility is a part of Petrikov mining and processing complex located in Belarus. The 64 meters high structure ensures the lifting of salt ore from the mine and its transportation to the factory for further processing. The ground part of the shaft is a massive concrete head. Our structure rests partly on the ground and partly on the concrete head. The deformation state of the structure is determined by the loads associated with the operation of lifting equipment, environmental factors, and interaction between the structure and foundation. Here we present the elements of the structure and the main operating loadings. The first stage of creating our monitoring system was the analysis of the stress-strain state of the structure formed under the action of indicated loads. As a result of the simulation, the maximum stresses and local deformation in the main structural elements were analyzed, and the possibility of buckling structural elements was also assessed. Based on this simulation, the main monitoring parameters were selected. They are settlement of load-bearing columns, then deformation in the lower part of the bearing columns, then deviation of upper part of the structure, temperature of main structural elements, and vibrational characteristics of the structure. This slide shows a diagram of main path of monitoring system. Here you see the blocks of primary sensors for recording quasi-static and dynamic processes, then the unit for data acquiring, processing, and transmission, and the unit for analysis and visualization of obtained data. Registration of monitoring data is controlled remotely from the city of Perm, Russia. Accumulation and processing of monitoring data are performed on the central server located in Perm. Monitoring results are presented on website. Authorized persons have an access to this site, and they can assess the current situation and then make administrative decisions. This slide shows the title page of our website, where we see the main measuring units. In each unit, the current information is given and compared with the maximum permissible values. The next series of slides show website pages with information related to each primary sensor unit. You can see the location of each group of sensors by structural elements and the history of data changes for the selected period. Next slide shows the operation of the unit of monitoring and even settlements of bearing columns. This slide shows the history of settlements for 15 months of observation. And this slide shows the field of base displacements relative to the points located on the concrete head of the shaft. Looking at these pictures, we can see that different points of the foundation settle at different rates. In addition, settling occurs unevenly over the time. Next group of slides shows the work of inclinometry unit. 8 inclinometers are placed at different heights. Here you see 5 months evolution of tilt angles on structural elements at different points. Such location of the sensors made it possible to reconstruct the distorted special shape of the structure. If we know the actual shape of the structure, we can evaluate an important control parameter, the deviation of the highest point of the structure from its original position. The next group of slides presents the work of strain gauges. Sensors are placed at the base of supporting columns in accordance with plan represented in this slide. This slide shows the reading of some sensors for 5-day and 5 months periods. Our observations have shown that the strain gauges reflect changes in the structure at different time scales. Thus, the reading change according to the daily temperature fluctuations. At the same time, the readings of some sensors respond to structural vibrations caused by technological operations. In addition, significant changes in the deformations were observed over a long period. Here we see the operation of temperature measurement units. A special role in our system is assigned to monitoring dynamic deformation processes. The structure is subjected to vibrations in a wide range of frequencies caused by technological equipment operation. The analysis of these vibrations can provide rich information about the integrity of the structure or about the appearance of damages in it. Our system uses 2 groups of vibration sensors, high-frequency accelerometers and low-frequency seismic sensors. Here you see the vibrograms obtained at different stages of technological cycle. The software included in the monitoring system processes the obtained vibrograms using the wavelet transform. The results are presented on this slide. In conclusion, I would like to point out the following. The developed monitoring system allows online control of the deformation processes in the metal high-rise structure caused by the action of different quasi-static and dynamic factors. This monitoring system has been successfully operating for 3 years. Data of quasi-static measurements are taken once every 10 minutes. Dynamic measurements are made once a day. The accumulated and incoming experimental information provides an assessment of the current deformation state of the structure. In addition, it becomes possible to predict the development of deformation processes for about 1 year in advance. Now we plan to further develop our system in this direction. We found some problems that appeared during the operation of our system. One of them is a decrease in the reliability of some elements caused by presence of sawdust in the environment. We are currently working on this problem as well. At this point, I would like to end my speech. Thank you for your attention. This slide presents our team and our institute and our city. Thank you for your attention.
Thank you.